Hello, I'm Max and we'll be presenting our work regarding an advanced characterization of a sensor system for droplet-based microfluidics. Microfluidic setups are most used as lab-on-a-chip devices with multiple advantages in comparison to conventional lab setups. Droplets can be used to encode information such as sample identification tags, but require microfluidic sensors for decoding. Previously presented sensor devices typically require complex lab setups or do not allow for color sensing. We therefore constructed a new optical sensor device that is cheap, portable, and easy to operate. The device can detect droplets and measure multiple parameters using an infrared and a color sensor. In the overall setup, the microfluidic channel, displayed in gray, is positioned above the infrared and color sensors. These in turn are aligned with the appropriate light sources. Droplets are generated by injecting colored ink at a T-junction. Both the continuous oil phase and the dispersed phase are driven by a pressure-controlled pump. Using both sensors simultaneously, the length of droplets in the microfluidic channel is calculated as a function of droplet velocity and duration. We use the video processing software Droplet Morphometry and Velocimetry for droplet length validation and estimated linear correction factors using a sample set of 45 droplets. The remaining sensor error for a test set of 70 droplets after application of the correction factors is shown here. In most cases, it is smaller than 0.5 mm. There appears to be no correlation between droplet size and measurement error. To investigate the spectral sensor's capabilities, droplets with 126 different colors were sampled. Each droplet consisted of a mixture made up of the fundamental colors cyan, magenta, and yellow. The transmitted color symbols were decoded using machine learning and a linear regression algorithm. Finally, the accuracy of color detection was calculated as detection offset using a further dataset. You can see the resulting detection offset for each value of the color alphabet. The position of the data points represents the actual color composition of the droplet. The color coding shows the detection offset that is less than 17% for most colors. The average offset for the whole color alphabet is 10.1%. In conclusion, a typical precision of 0.5 mm was achieved for droplet size detection, allowing for the transmission of data encoded in droplet length. Furthermore, this functionality allows for real-time control of droplet on-demand setups. An alphabet of 126 different colors was successfully transmitted, enabling color-coded data transmission. The color detection capabilities could also be used to analyze color reagents, for example, to determine the pH value of a droplet. Thank you very much for your attention.